Hey everybody, in this video I want to mention the Heisenberg uncertainty principle. It gets a lot of press in quantum mechanics, and it is a neat thing to talk about. It's not as useful in terms of engineering and designing with quantum mechanics. It's more of a statement, a restatement really, a statement in a different way of the wave-particle duality of matter, in particular its wave-like nature. It does, though, represent a way to state that there is probability in the universe, which is hallmark of quantum mechanics. You can't say for sure with 100% certainty what's going to happen in a physical interaction. So it's a way to state that, which is it is an important statement philosophically and in terms of our model. But again, as far as engineering with it or predicting the behavior of a system, it's not as useful as other things like the Schrodinger equation, which we'll talk about in the next video. All right, so let me stop blabbing about why it's not as important as the Schrodinger equation, but it's still important, and let's talk about it. So the idea at the time, remember with de Broglie's postulates and this whole beginning of quantum mechanics, treating particles as waves, some people realized that there were some implications about the physical universe. Heisenberg was one of them. And let me set this up by doing something very special. We're going to consider a very special experimental measurement. That's where we're going to have a measurement of a particle's position and its momentum at the same time. Again, that's a very special case. But let's suppose we're going to do an experiment where we wanted to determine the position of a particle and its momentum. Okay, so what I mean then is, in terms of symbols, let me scroll down here. There we go. Let's suppose something is traveling, let's call it the x direction, right? Now, as a particle, in what we sometimes call classical physics, if you wanted to measure, let's say this is the x-axis, where it is, and its momentum. So we have mass times velocity is its momentum. Let's say that the uncertainty in the position is x, is delta x. So I'm going to write it like this, x plus or minus delta x. And let's say there's an uncertainty in the momentum. So I can say the momentum is measured to be p plus or minus delta p. In classical physics, if your equipment is really, really, really good, you could make this uncertainty be arbitrarily small in position and arbitrarily small in momentum. Now again, you're trying to determine these at the same time. And I just remind you that P is equal to mv. Okay, so if you're measuring these at the same time, with classical physics, with really good equipment, you could make both uncertainties arbitrarily small. What Heisenberg figured out and stated was that's not true in reality if you treat these as waves or treat this as a wave. So if this is treated as a matter wave, again, that's my picture of what it, quote, looks like, right? This particle is spread out over some finite distance, right? Because it has wave-like nature. It's not isolated at one spatial point. Okay? And what Heisenberg argued is, look, if you want to measure this spatial extent really, really, really well, then what, so in other words, that should be minus, you want to make this delta x really, really, really small. Right, so basically you're trying to shrink this region and you're trying to locate this particle to, in the limit, right, to one spatial point. In that process, you lose information about its wavelength, right? You need some distance to accurately determine its wavelength because it's spread out, right, over some distance. So to get an accurate determination of its wavelength, you can't just be focused on some arbitrarily small spatial distance. So what he realized is, as this uncertainty in position is going down, the uncertainty in its wavelength is going to be going up. You're losing accuracy in measuring that wavelength if you are making this delta x go down. So as the uncertainty in the wavelength goes down, the uncertainty in the wavelength is going up. So you can imagine that you're trying to measure the wavelength with a plus or minus uncertainty. This uncertainty is getting bigger if the uncertainty in position is getting smaller. Now, what Heisenberg says is that, and look, we know that the momentum of the particle is directly related to its wavelength, right? That's one of de Broglie's postulates. A measurement of wavelength is a measurement of momentum. So this uncertainty in wavelength, that translates to an uncertainty in momentum. So if the uncertainty in position is going down, the uncertainty in the momentum is going up. You can't have it both ways. You can't arbitrarily make delta x and delta p small. As one's getting smaller, the other's getting larger. Now, we're not going to work out the details, but he did the math. In fact, he used Fourier analysis, which you guys may have talked about in, I don't know, Calc 2 maybe, okay? In Fourier synthesis, you can make any function you want by adding up enough harmonic waves, cosines and sines, and that's what he used. But what he was able to show is that there is a trade-off between these two uncertainties, and in fact, you can write this as a minimum product of the two. And this is usually written like this. This is h bar over 2, okay? That's again h bar. Remember, h bar is h over 2 pi. That's shorthand. So what he was able to show is that even with perfect equipment, there is a minimum product of delta x, delta p. That minimum product is going to be h bar over 2. The greater sign is here. That's because you may have really bad equipment, right? So it may be that the uncertainty product is much larger than that just because of your equipment. But the critical part is this equal sign. What Heisenberg says is a simultaneous measurement of position and momentum is going to give you a certain level of uncertainty, even with perfect equipment. This is a very radical statement from classical physics, which says that with perfect equipment, you should be able to make delta x and delta p basically vanish. With a simultaneous measurement of these two, you should be able to make them vanish, the uncertainties. Heisenberg says, nope, that's not how nature works. Because of this wave-like nature of matter, there is not an arbitrarily small uncertainty in a simultaneous measurement of position and momentum. Now you may say, well, who in the heck's going to do a simultaneous measurement of position and momentum? And I hear you. You're right. You're not going to usually design an experiment to do that. But if you did, you are limited by the wave-like nature of matter. You're limited by nature as to how well you can determine those two quantities simultaneously. So it is an important statement. Now, you can do a similar analysis, but instead of position and momentum, you can talk about it in terms of energy and time. So you might, for instance, say, okay, suppose I excite an atom, right? Suppose I go from one lower energy level to a higher energy level. Maybe it's by absorption of a photon. So the atom is, and this is an example, but the atom is in an excited state. Well, suppose you want to measure the energy of that excited state with a plus or minus delta E, right? But you also want to know how long is it in that excited state. So you're doing a simultaneous measurement of how long the atom is in this excited state before it undergoes a transition and maybe spits out a photon in a decay. Okay, so again, this is a simultaneous measurement. Well, again, what Heisenberg said is, look, a measurement of energy, if we think of the de Broglie postulates, right? The frequency is the energy over Planck's constant. So if we treat this atom as a wave, not as a particle, right? And also, look, this could be an electron in an atom. So you could be exciting the electron to a higher level. So you could be talking about the electron itself. But the point is that the energy is directly related to the frequency of the matter wave. Okay, so a measurement of energy is really a measurement of frequency. The reason that's important is because frequency is related to time, right? Look, let's say I'm trying to get delta E as small as possible. That means you really want the uncertainty in the frequency of the matter wave to be really small, right? Well, how do you do that? How do you measure frequency? Frequencies are going to take some interval of time to determine. So if the uncertainty in the frequency is going down, the time that the delta t, right? The time interval that you're using to measure those frequencies is going to be getting larger and larger, because you want to make sure that you are measuring the frequency really well, right? So that means you're going to have more cycles than just one. But more cycles measured means the time interval used is getting larger and larger. So as the delta f, the frequency, goes down, the corresponding delta t is going up simply because you're using longer and longer time intervals. So there's a trade-off in delta f and delta t, the uncertainty in the frequency and the uncertainty in the time. But the frequency is directly related to the energy, so there is a trade-off between the uncertainty in the energy and the uncertainty in the time that this particle has this energy. And if you do the analysis, it turns out that the product of those two uncertainties, the smallest it can be, is also h bar over 2. So we usually write it like this. The greater sign again means you may have equipment that's not great equipment, so the uncertainty product is larger than h bar over 2. Again, the important thing is this equal sign. With perfect equipment, you still are going to be limited. If you try to measure simultaneously the energy of a particle, like for instance an atom or an electron, and the time it has that energy. Okay, so again, Heisenberg uncertainty product, this time written in terms of energy and time. Again, philosophically, this is a very different statement than classical physics, where if you have perfect equipment, you should be able to get delta E and delta T arbitrarily small. Now, you can do a calculation example. You can see that right here. Suppose the speed of an electron is measured to be 10,000 meters per second with an uncertainty of 0.01%. I represented the uncertainty as a percent. What if you wanted to determine where is the electron, measure its position at the same time you're measuring this speed to within 0.01%? What would be the smallest uncertainty in this position if you had perfect equipment and were only limited by nature, right? So the way that would look is, let's do it on my notepad. Scroll down, get me some more room here. So in this example, and I'm going to go through this fairly quickly. So we have a speed of 10 to the 4 meters per second, right? 10,000 meters per second. And delta V over V, because I give it to you as a percent, So delta V over V is 0.01%. I believe it was 0.01, correct? Yes, is 0.01%. So you can convert that to a decimal. That would be 0.0001. Okay? So the question is, if you're going to measure the position to within plus or minus a certain delta x, what is this delta x? So what you could do is you could use the Heisenberg uncertainty principle statement, delta x delta p is greater than or equal to h bar over 2. Now we have to figure out delta p. So what you would do is you would say, okay, look, delta p is going to be m times delta v. That comes from the fact that momentum is mv. So if there's an uncertainty in v, there's going to be an uncertainty in p, and actually you can use calculus to demonstrate this. If I look at dp dv, I just get m. So if I think of dp as a delta p and dv as a delta v, I just get m delta v. I mean, another way you can do this is, look, you could say, let me calculate the momentum using mv, and then let me change v by 0.001 and recalculate and add and subtract and calculate the new momenta. You're going to get the exact same thing, okay? Delta p is going to be m delta v. So what I can do then is, for that delta v, I can put in, oops, I just got rid of that. Ha, I hit my button on my stylus. Let's do it again. So delta p is, oh, and it just came back. Oh my gosh. Crazy. There we go. Delta p is m delta v. So I would put in for delta v 0.0. Yes, I know. I'm having trouble with my stylus. So I would have equals m times 0.0001 times v. I'm just using the delta v over v is 0.0001. So delta v is 0.0001 times v. So my corresponding delta p, right, is going to be 0.0001 times the mass. So this is an electron, right? 31 kilograms times my v, 10 to the 4 meters per second, and that's a 4. Right? And you're going to get some value right here. In fact, that's going to be 10 to the minus 4. Oh, that's actually going to be 9.11 times 10 to the minus 31 kilogram meter per second. Okay? Then what you do is you say, okay, so delta x from the Heisenberg uncertainty principle statement, delta x is going to be greater than or equal to h bar over 2 over delta p. Put in the numbers. I guarantee, which means I'm probably wrong, 0.058 millimeters. So this will turn out to be, if you put in all SI units, 0.058 millimeters. Okay, so if you were going to measure the position of this electron simultaneously at the same time that you measured its speed to be 10 to the 4 meters per second plus or minus 0.01%, the best you could do in pinpointing its position would be 0.058 millimeters plus or minus, whatever x is, right? I mean, x ended up being, I don't know, 20 millimeters on my scale. Well, that would be plus or minus 0.058 millimeters, okay? Again, that's just an example of how you could use the Heisenberg uncertainty principle. I realize this is a very concocted example. All right, again, people aren't usually measuring position and momenta at the same time. Okay, so be familiar with the statements of the Heisenberg uncertainty principle. What they mean, again, they mean simultaneous measurements, right? A position and momentum. There's going to be a certain limit to how well you can measure those simultaneously. Similar for energy and time. I doubt I'll give you a problem on a test where similar to this example where you're using the uncertainty products to calculate a delta x or a delta t or whatever. Okay, I'm going to end it. Enough. Goodbye.